Welcome everyone and welcome to the first video in our series, AI Pro Series, Mastering Advanced Techniques. Today, we're diving headfirst into the thrilling universe of deep learning, a potent subset of artificial intelligence that's revolutionizing our world in ways we could hardly imagine a few decades ago. Deep learning takes its inspiration from the structure and workings of the human brain. Picture billions of neurons, each connecting with thousands of others, forming a complex, dynamic network. This intricate system allows us to think, learn, and make decisions. Now, imagine if we could design a machine that mimics this process. That, in essence, is deep learning. Just as our brains learn from experiences, deep learning models learn from vast amounts of data. They sift through this data, identify patterns, and use these patterns to make intelligent decisions. Whether it's recognizing a face in a photo, translating a foreign language, or predicting the next big trend in the stock market, deep learning is the powerhouse behind these capabilities. But how does deep learning achieve this? At the heart of deep learning is a concept called neural networks. These are algorithms designed to recognize patterns, much like how our brain's neurons work together to process information. We'll delve deeper into this concept in our next scene, exploring the intricacies of neural networks and how they form the foundation of deep learning. Deep learning is a vast and fascinating field, with its roots in human curiosity and its branches spreading into virtually every sector of modern life. From healthcare and finance to entertainment and transportation, deep learning is transforming the way we live, work, and play. So buckle up as we embark on this exciting journey into the world of deep learning. We'll demystify complex concepts, unravel the workings of neural networks, and explore innovative applications of this technology. It's going to be a thrilling ride, filled with insights, discoveries, and perhaps a few aha moments. So Sarah, are you ready to explore the building blocks of deep learning? Let's start with neural networks, the foundation of deep learning. Picture a vast web of interconnected processing units, not unlike neurons in the brain. These units, aptly named artificial neurons, are the basic building blocks of neural networks. Each neuron receives information, processes it, and passes it on, creating a dynamic flow of data. The information they process isn't just random noise, though. It's filtered through connections or synapses, each carrying a different weight. These synaptic weights determine the influence one neuron has over the next. Now let's delve a bit deeper into how these neurons work. Each neuron sums up the information it receives from other neurons, applies a function to this sum, and sends the result out to other neurons it's connected to. This function, known as an activation function, is what decides whether a neuron should be activated or not. It's a bit like the neuron's decision-making mechanism. The activation function is vital for neural networks to learn complex patterns. Without it, the network would only be able to learn linear relationships in the data. But with it, the network can learn to identify intricate patterns, even in vast amounts of data. But how does a neural network learn? It all starts with random synaptic weights. At first, the network is like a newborn baby, knowing nothing about the world. But as it's exposed to more and more data, it starts to adjust its synaptic weights. This is a process called training. In the training phase, the network is fed a large amount of data, along with the correct answers or targets for that data. This could be anything from images of cats and dogs, to stock market data, to audio files. The network makes predictions based on its current synaptic weights, and then compares these predictions to the targets. If the predictions are off, the network adjusts its weights to reduce the error. This is done through a process called backpropagation, which involves calculating the gradient, or slope, of the error with respect to the weights, and then adjusting the weights in the direction that reduces the error. This process is repeated many times, with the network continually adjusting its weights in response to the errors it makes. Over time, the network learns to recognize patterns in the data. It might learn, for example, that certain pixel patterns are associated with images of cats, while others are associated with dogs. The beauty of neural networks is that they can learn to recognize these patterns without being explicitly programmed to do so. They learn directly from the data, making them incredibly powerful tools for tasks like image recognition, natural language processing, and even playing video games. But neural networks aren't just powerful, they're also incredibly flexible. They can be designed with different architectures to suit different tasks. For example, convolutional neural networks are great for image recognition, while recurrent neural networks excel at processing sequential data like text. In essence, neural networks provide the foundation for deep learning, enabling machines to learn from experience much like we do. They represent a significant step forward in the field of artificial intelligence, bringing us closer to the goal of creating machines that can truly understand and interact with the world. By adjusting these weights through a process called training, the network learns to recognize patterns in data. Opening. So, Sarah, can you explain in your own words what a neural network does? Well, let's hear from Sarah. Sarah, you have the stage. A neural network, she begins, is like a team of tiny experts, each working together. Each unit or node in the network processes a piece of information, and by adjusting the strength of their connections, they learn to identify specific patterns. Bravo, Sarah, that was a spot-on explanation. Just to reinforce, it's important to remember that these tiny experts Sarah mentioned are the neurons in the network. These neurons receive input, process it, and pass it on. The stronger the connection or weight between neurons, the more influence they have on each other. This weight-adjusting process is what we call training. During training, the neural network learns to recognize patterns in the data it's been given. It's like a detective piecing together clues to solve a mystery. The more data it receives, the better it becomes at recognizing these patterns. Let's take the example of a neural network learning to differentiate between images of cats and dogs. It starts by recognizing simple features like edges and shapes. As it receives more and more images, it begins to understand more complex features. Over time, it becomes efficient at telling cats and dogs apart, all thanks to the process of training. So in essence, a neural network is a system of neurons working together to make sense of data. It's like a mini-brain, learning from experience and making intelligent decisions based on that learning. To sum up, Sarah, your explanation was spot on. Neural networks indeed work like a team of experts, each processing a piece of information to identify patterns. Through training, they adjust their connections to learn and grow, just like us humans learn from our experiences. Closing. That's a great explanation. Now, there are different types of deep learning architectures designed for specific tasks. These architectures form the cornerstone of deep learning, each with its own unique design and purpose. Today, we're going to discuss three main types of deep learning architectures: convolutional neural networks, recurrent neural networks, and generative adversarial networks. So, fasten your seatbelts as we embark on this fascinating journey. Let's start with convolutional neural networks, or CNNs. CNNs are the go-to deep learning architecture for tasks involving images. They are inspired by the biological processes in the human visual cortex, the part of the brain responsible for seeing. CNNs excel at identifying patterns within images, patterns like edges, curves, and textures that help us distinguish one object from another. For example, a CNN can be trained to recognize faces in photographs by learning to identify features like eyes, noses, and mouths. It's like teaching a machine to see and understand the visual world just like we do. Next, we have recurrent neural networks, or RNNs. If CNNs are designed to understand spatial patterns in images, RNNs are designed to understand temporal patterns in sequences. This makes them perfect for tasks involving sequential data like text, speech, or time series. RNNs have this amazing ability to remember previous inputs in a sequence and use this information to influence future predictions. For instance, in machine translation, an RNN can analyze the relationship between words in a sentence, taking into account the context to provide an accurate translation. It's as if the network is reading and understanding the text, word by word. Lastly, we have generative adversarial networks, or GANs. The concept of GANs is a bit like a forger and a detective locked in a constant battle. In a GAN, there are two neural networks, a generator and a discriminator. The generator creates new data, while the discriminator tries to distinguish real data from the data created by the generator. The generator constantly tries to fool the discriminator, and in doing so, it gets better and better at creating realistic data. An example of GANs in action can be seen in how they can generate realistic images of people who don't even exist. It's like watching a suspenseful game of cat and mouse, where the players are getting smarter with each round. But these are not the only architectures out there. There are many more, each with their unique strengths and applications. Some are designed for specific tasks like speech recognition or text generation, while others are more general purpose and can be applied to a wide range of problems. Each architecture has its own way of processing information, learning from data, and making predictions. The choice of architecture depends on the task at hand. If you're dealing with images, you might want to use a CNN. If you're dealing with sequences or time series data, an RNN might be a better choice. And if you're looking to generate new data, a GAN could be the way to go. Deep learning architectures are truly fascinating. They are inspired by the human brain, yet they are capable of learning and understanding complex patterns in data that even humans struggle with. They are powerful, versatile, and have a wide range of applications, from recognizing faces in photos to translating languages to generating realistic images. So the next time you see a deep learning model in action, remember that behind the scenes, there's a carefully designed architecture, learning from data, recognizing patterns, and making intelligent decisions. These are just 3 types of deep learning architectures, each with their unique strengths and applications. Let's try a quick activity. Imagine you're building a convolutional neural network, or CNN, to classify handwritten digits. There's a myriad of squiggly lines, curves, and loops, all forming the numbers 0 to 9. Now, how would you go about this? What kind of features would you want your network to focus on? Take a moment to visualize. A 0 is essentially an oval shape, isn't it? It's a continuous loop without any sharp edges. So your CNN might need to recognize this loop shape. But what about a 1? It's mostly a straight line, isn't it? So straight lines might be another feature your network should be able to identify. Now, think about a digit like 8. It's a bit more complex, isn't it? It has 2 loops, one on top of the other. So your CNN might need to recognize not just individual loops, but also their arrangement. And then there's 4, with its sharp angles and intersecting lines. Your network might need to recognize intersections as well. But how about the number 9? It's a loop and a line, isn't it? So your network might need to recognize combinations of these features, and so on for the other digits. Each one has its own unique combination of loops, lines, and intersections that your network will need to learn. By identifying these key features, your CNN can start to make sense of the different digits. It can learn to recognize the loop of a 0, the straight line of a 1, the intersecting lines of a 4, and the combination of loop and line in a 9. And that's just the beginning. Once your network can identify these basic features, it can start to combine them in different ways to recognize more complex patterns. It's like learning the alphabet before you start forming words and sentences. Identifying these key features is an important step in training our CNN. It sets the foundation for our network to build upon as we feed it more and more data, and it learns to make increasingly accurate classifications. So the next time you see a handwritten digit, think about all the different features your brain is automatically identifying. It's pretty amazing, isn't it? Now, training these complex networks requires optimization techniques to adjust weights and improve their performance. This is where the magic happens as our neural networks begin to learn and adapt. It's like teaching a child to ride a bike. At first, they may wobble and fall, but with each tumble, they learn how to balance better, how to steer, and how to pedal efficiently. Similarly, in the realm of deep learning, we have a special technique called backpropagation, which is the backbone of training deep neural networks. Just as the name suggests, backpropagation involves propagating errors back through the network. It's a way of fine-tuning the weights of the network based on the error rate or the difference between the predicted and actual output. Picture this: you have a layered cake, and each layer of this cake represents a layer in our neural network. Now, when you feed data into this network, it goes through each layer, gets processed, and finally produces an output. But here's the kicker. This output may not match the actual or desired output. That's where backpropagation steps in. Backpropagation, in essence, is like a feedback loop. It calculates the error at the output and then distributes this error back through the layers of the cake, or in our case, the neural network. This error is then used to adjust the weights in each layer, helping the network learn from its mistakes. Imagine our network as a student and backpropagation as a diligent teacher. When the student makes a mistake in a test, the teacher doesn't just mark it wrong and move on. Instead, the teacher shows the student where they went wrong, explains the correct solution, and guides them on how to avoid the mistake in the future. Just like the teacher-student interaction, backpropagation identifies where the network made an incorrect prediction, pinpoints the weights that led to the error, and then nudges these weights in the right direction. With each iteration, the network learns a bit more, inching closer to the correct solution. Let's consider an example. If our network is learning to recognize handwritten digits, it might initially struggle to distinguish between a sloppy 7 and a 1. But with backpropagation, it learns from its errors. It adjusts its weights. So next time when it sees a similar 7, it's more likely to classify it correctly. Backpropagation is not a one-time process. It's iterative and continues until the error rate is minimized and the network's performance is optimized. It's like the teacher who tirelessly works until the student masters the subject. And that's the beauty of backpropagation. It's a powerful method that enables our neural networks to learn, adapt, and evolve, thereby making deep learning a reality. So remember, backpropagation is like a teacher guiding the network, showing it where it went wrong and how to improve. It's the secret sauce that makes our neural networks truly intelligent. This is just a glimpse into the fascinating world of deep learning. Today, we've journeyed through the intricate layers of this powerful artificial intelligence subset, starting with the very foundation, neural networks. We've seen how these networks mirror the structure of our own brains, with interconnected processing units functioning like neurons, receiving, processing, and transmitting information. We've also delved into the crux of the learning process, training. The weights of the connections between these units are meticulously adjusted, enabling the network to learn from experience, to recognize patterns in data, and to make intelligent decisions. This process, akin to the way our brains learn from experience, is what makes deep learning so powerful. Moving beyond the foundation, we've explored the various architectures of deep learning, each uniquely designed for specific tasks. The convolutional neural networks, or CNNs, which excel in image recognition. The recurrent neural networks, or RNNs, which are adept at handling sequential data such as text. And the generative adversarial networks, or GANs, which involve two competing neural networks, a generator and a discriminator, working together to improve. We've seen how these architectures are trained, with optimization techniques like backpropagation guiding the network, showing it where it went wrong, and how to improve. This is akin to a teacher guiding a student, pointing out the mistakes and showing the way forward. But this is just the beginning. The world of deep learning is vast and still largely unexplored. As we continue to delve deeper, we will discover more about this fascinating field, its potential, and its power. We'll understand how it's shaping our world, influencing everything from our daily interactions with technology to groundbreaking scientific research. Stay tuned for more in-depth discussions in our next videos. As we continue to explore this fascinating field together, we'll unlock the mysteries of deep learning one layer at a time.